Okay, good morning everybody. So I'm going to give you a bit of just an introduction before we start the tutorial, just to check everybody has fired up their virtual machines. Yeah, that's the practical is going to be done in Snap, which you used with TJ on Tuesday, I think it was. So if you get logging into that now, because I know it takes a little bit of time to start up, so we're going to use that. Okay, so I'm going to talk to you a little bit this morning about how we can use ocean colour data to detect harmful algal blooms in coastal waters. So this is based on work that I did during my PhD, and we're going to look at a nice example from South Africa in the tutorial. So we'll start with what are HABs. Some of you may already kind of know a bit about them. It's kind of a loose definition actually. You kind of have them as blooms of algae that cause harm in some way to marine and other life, so including what's in the sea and us. And they can have both natural and unnatural drivers. So they can occur naturally due to the type of ocean circulation you've got going on, or they could be as a result of influx of nutrients from land, for example, your eutrophication, you may have heard it called, that sort of phenomena. There's two main mechanisms by which they cause harm. There's lots of sort of finer details of this, but the two main ones that I'll discuss are biomass related. So often harmful algal blooms are really, really big growths of algae. And then you can have problems with anoxia. So when the blooms grow, they die, they decompose, and the oxygen gets stripped from the water. This is not ideal if you're a fish, a lobster, something like that, living in the coastal region, as in this case here. These are all lobsters that have walked out of the sea when they've had an anoxic event as a result of a HAB. There can also be physical impacts of these high levels of biomass, for example, from gill clogging of fish. The second, oh, have I gone back? The second major source of impact is the toxicity. And this is then related to the specific species of algae, or I'm not touching anything. Oh, it's a PDF, so it shouldn't have anything fancy on it. Let's go back. So the toxicity is related to the individual species of algae or phytoplankton that are in the blooms. And so this can happen then at low concentrations, and this makes it a little bit more difficult to detect from a remote sensing perspective. This is really Okay. I'm like, this is tripping me up a bit. Okay? Right. Okay, I think we're good. Okay, so yeah, toxicity can happen at low concentrations of these species, so that makes it quite difficult to detect because things will just die or potentially get poisoned. This is often what is the case when you get shellfish poisoning. So if you've ever eaten shellfish and got sick the day after, it can be as a result of types of toxic algae that have got into those shellfish and caused these impacts. So yeah, HABs have a potential to impact marine life, also the potential to harm our human health, and as a result of that can affect industry quite strongly. So there's quite a sort of socio-economic driver for us to understand this phenomena. Particular things that can be affected are tourism. I mean, these guys are swimming in that. I wouldn't want to swim in that. But you know, so if you're at a beach, that's not really what you want for your swimming conditions. And aquaculture is another particular area of interest when it comes to harmful algal blooms. So a lot of what we're doing when it comes to working with remote sensing in this context is to help support these industries, provide warning systems, or to manage the impacts of these blooms. So what do we need in order to monitor HABs? Well, there's several sort of main sources of information which we need, and remote sensing can help us in get these. So we need accurate information about the blooms at the temporal and spatial scales at which they form. So this can be from sort of daily event scale, time-wise, up to interannual. We might want to know, for example, do they happen at a particular time of year, or are they increasing in their severity or in their prevalence? How often are they happening? So we need something that spans that wide range of timescales, and we also need something that spans suitable spatial scales. So you'll have seen those pictures before. Often this is quite a like a coastally constrained phenomena. It's where we're interacting with the sea most directly. So we need data that can capture that sort of scale as well, so quite fine scale. Ideally, we want an ability to detect and track high levels of biomass associated with these blooms, which causes those anoxic events that I previously mentioned. So you need to be able to quantify, for example, the chlorophyll at quite high levels. And ideally, we'd like an ability to distinguish between different species so that we can understand if there's going to be a potential for harm from toxins, for example. And also to understand how and why different species might dominate from a sort of more science and research perspective. But there are some challenges to using remote sensing in these regions. So you can imagine having a 10-year archive of satellite data. You could start looking at those interannual scales, and with new sensors such as Sentinel-3, which is at 300-meter resolution, you can start looking into coastal bays. So you do need high resolution. So this will affect the choice of sensor you might select to investigate these phenomena. So you might want to have a preference towards the sort of more spatially higher resolution sensors. But you still need to balance that up with the temporal resolution. So because these blooms can happen over sort of day timescales, maybe within a week, you need to have quite frequent images coming through so you can see how they're changing, where they're moving. So you then need to also have a sensor that's coming over quite regularly. Again, in this case, Sentinel-3 is quite a good call for that, because you've got a balance between fairly high resolution at 300 meters spatially and every couple of day revisit time, possibly more when you've got the other sensors flying on the Sentinel program. And then the last point there is, in terms of resolution, is about spectral resolution. So you'll see in the practical some examples of in situ radiometric data, which is very similar to what the satellite is capturing when we talk about ocean colour, the spectra of the colour throughout different wavelengths. And different satellite sensors have different bands, as we call them. And where those bands are placed will influence whether you could pick up, for example, spectral signatures that are specifically related to different types of species, or may influence whether you can apply certain types of algorithms. So these are all things to consider when you're choosing what data you want to work with for HAB monitoring. Coastal regions themselves present a problem. They're usually optically complex, we call them. So what that means is that, for example, chlorophyll is not always the dominant part of the signal. You may also have input from the land, you might have rivers, and generally the conditions there might not be the conditions that would be most representative for the algorithms that have been developed to look at global satellite data. So you might have to consider that. And the other thing you may need to consider is that when you get very close to the coast, you have issues with things like the aerosols not being as well modelled or more variable, so your atmospheric correction might not be so easy. You could also have what they call the adjacency effect, where you've got very bright land, which will contaminate your pixels here very close to the coast, which your ocean is comparatively dark compared to your land. So one of the things that's really crucial when you want to work in these areas is to think about what we call validation. And we're going to do a little bit of validation in the practical. So it's looking at how does the in situ data you've got match up with your satellite, and checking, is the quality of the satellite data good enough for me to start making some assumptions about what's going on in the water. And if not, how can I use that in situ data to maybe create a new algorithm that might help me? So this example I always show summarises that quite nicely. This is just a standard chlorophyll image out of the MERIS sensor. And you can see there's this big white patch through the middle there. Now, that's actually where there was a huge harmful algal bloom. But if you just look at the standard product, you don't have that data because the algorithm there has failed, the atmospheric correction has a problem as well. So you have to think about, how can I use this to then get some information back? I mean, that's a pretty big hint that something interesting is going on, but it doesn't necessarily help you to quantify things. So I'm going to present to you an ideal case study. This is an area very close to my heart. This is where I did my PhD, in this lovely area here in the southern Benguela. It's a very dynamic, upwelling-driven region. So the harmful algal blooms that occur there occur completely naturally as a result of the upwelling winds, which drive nutrient influx into the surface waters. They have very high biomass blooms, as I put there, up to 2,000 milligrams of chlorophyll recorded, really, really big. So it's a really good case study area to look at these types of blooms. And many examples we have from in situ data there of monospecific blooms. So these are individual blooms are dominated by individual species. And you can see that in these spectra here. These are related to different blooms dominated by a single species. And you can see the different shapes that you get. So you can start thinking about how you'd use that data to inform maybe an algorithm. It's also incredibly important as an area for South Africa's national fishing and aquaculture industries. And as I said, it suffered historically from these blooms quite a lot. You can see some examples of them in this bay here, the red being the high chlorophyll. So generally, yeah, there's a great need and opportunity here to both understand the sort of science of the remote sensing, but also a need to develop these techniques to help manage the resources that are really important in a development context. So what are we going to do today? In terms of the tutorial, we're going to go and work with SNAP again. So you've already done a little bit with this, which is great. So we've got a bit of a head start on that. I'm going to use SNAP to assess some data and apply some different techniques that might be useful for you to look at how suitable data is for the detection of high biomass HABs in particular. We're not going to look too much at species toxicity, focusing more on the high biomass anoxia-related HABs today. You're going to work with several different types of data, so predominantly MERIS. This is the heritage instrument that has sort of led to the development of the ALTSHE sensor, which is now flying aboard Sentinel-3. We're working predominantly with MERIS because I have a lot of in situ data to go alongside it, because ALTSHE's not been up there for so long, we don't have the same amount of in situ data. But there is also ALTSHE data from a more recent bloom for you to explore as well during this tutorial. There's also, for comparison, some imagery from the MODIS sensor, which has a really good long time series. It's still going today. It's soldering on despite being quite old now. But it has lower resolution in terms of the spatial scale and in terms of the spectral resolution for these sort of monitoring purposes. You've also got a spreadsheet there of in situ radiometric data and some chlorophyll data. So you're going to look at a little bit of how you validate some satellite data with that. So things to understand what a HAB may look like from an in situ and satellite ocean color perspective, how the process of satellite validation works using in situ data, what the quality flags mean for data, and how you can link those with your understanding of a system to figure out what the discrepancies are between in situ and satellite-based data. And I hope you can maybe start to understand a little bit about why differences in the instruments might result in the instruments on the satellites might result in differences between what you see by different satellites and compared to your in situ. You'd also then have a look at applying a custom empirical band ratio algorithm. So you may have heard a little bit about these already this week, using blue and green ratios to estimate chlorophyll. In this case, we're going to use some red light to do this, which is useful in the context of these harmful algal blooms. So your spreadsheet has a little example of that an algorithm in there. Shows you how it's developed using in situ data for the radiometry and the chlorophyll. And it shows you how you can apply this algorithm in SNAP using the band maths expressions that you used earlier in the week as well. And then there's the last bit of the practical looks at spectral signatures. So there's a couple of interesting blooms of some unusual species that happened in this region. And they have quite a distinct spectral signature, which you can see very nicely in the in situ data, but you can also start to pick up in the satellite data. So you can have a look at that and consider how you might use those spectral shapes to create an algorithm. Okay, so you've got printouts on your desk of the PDF of the sheet. Hopefully that'll help you follow it. But that PDF, if you need to look in any more detail, is also on your machines. It's in the virtual machine, in the Ocean Color course folder, and then it's HAB Practical, I think, is the folder you're looking at. So that should be in there. Then you've got the Excel spreadsheet, and then you've got the different types of satellite data. The main files you'll see listed in your, on your sheet there are the MERIS ones, but then there's also these for you to have a look at as well. You've also got in there a book chapter, which was something we wrote about this area and about HAB detection there in particular, so it's useful for some background context if you wanted to do a bit more reading. And also for reference, if you wanted to look more into this topic, if you wanted to use Sentinel-3 data now to do this same sort of analysis in new areas, you can get that data from EUMETSAT via CODA. You've already used that a little bit this week. And if you want to start thinking about regularly processing this kind of data, I'd recommend getting involved in the SNAP forum and having a look at what their options are for command line processing, and also keeping up to date with the sort of in development parts of SNAP, which include things like atmospheric correction and new algorithms, and these are very likely to be useful for people who are wanting to do coastal HAB detection, things like that. You may also want to think a little bit about whether you could use Sentinel-2 and Landsat 8. These are much higher resolution spatially, but spectrally not quite so well suited for the ocean applications. But there is definitely potential for synergetic use between the two, between these two and Sentinel-3. There's also some processes available, such as Acolyte, which allow you to quite easily process this data so it can start being used in coastal regions. Okay, so if you'd like to start with the practical, I'll be around. So there's some little questions in there, sort of prompt you to think about things, but if you have any questions, just stick your hand up or grab me as I walk past.